Well, good morning. This is Miss Dagenford, and today we're going to be looking at the scientific method, more specifically, how to create testable hypotheses. Now, you hear a lot about the scientific method, and every book tends to talk about it, but really, um, they love to formulate it, but there's really no formula for discoveries that every scientist uses. What we want is something logical, rational, and something that can be testable. So let's take a look at some of the qualifications. Now, to do a good research experiment, you want to have a hypothesis that is testable and includes predictions. That's the first characteristic. So I have a quote. This is from a really nice website. Science proceeds by making observations of nature, experiments. If a hypothesis does not generate any observational tests, there is nothing that scientists can do with it. Arguing back and forth about what should happen or what ought to happen is not the way science makes progress. Consider the following hypotheses. Hypothesis A. Our universe is surrounded by another larger universe with which we can have absolutely no contact. We really can't make any observations about that. That is just rather useless. Right now, at least, we have nothing to measure that with. Hypotheses must be falsifiable. Now, this can be a little tricky, but you want to think about, you need to be able to prove it false. So here's another hypothesis, hypothesis B. There are other inhabited planets in the universe. This hypothesis is testable, but it's not a scientific hypothesis. Here's why. Hypothesis B may be either correct or wrong. If it is correct, we can figure determine that because of several things. We could have a space probe sent from Earth to explore the universe, and it sends back the news that it has discovered an inhabited planet. And then this is later confirmed. You could have radio telescopes on Earth beginning to receive signals from somewhere in the Andromeda galaxy that appears to be reruns of the I Love Telek show. And thirdly, we could have a visit. Knock, knock. Greetings, Earthling. I am Telek from the planet Zuron in the Andromeda galaxy. I have just landed in your backyard. Take me to your leader. So if hypothesis B is true, we can verify that. However, we can't really prove it false. If hypothesis B is wrong, there's no test that will prove it. If one of our space probes never finds an inhabited planet, it doesn't mean that one doesn't exist. If we never receive signals from space, or Telek never lands in your backyard, that does not prove that the hypothesis is wrong either. Hypothesis B is not falsifiable. How about this one? Hypothesis C. Any two objects dropped from the same height above the surface of the Earth will hit the ground at the same time as long as air resistance is not a factor. Now take a look at this one. Hypothesis C is a scientific hypothesis because it is testable. We can pick two objects and drop them. You may have to provide a vacuum, but you can do that. It is falsifiable, and here's the kicker. If you can find any two objects that don't hit the ground at the same time and can show that it is not due to air resistance, then you have proven the hypothesis wrong. This hypothesis sticks its neck out for every test. In theory and in practice, if hypothesis C were wrong, it would be very easy and straightforward to show it. As Popper pointed out, it is relatively easy to gather evidence for just about any idea, but a hypothesis is essentially worthless unless it is risky. It must make predictions that could contradict it. The process of gaining real confidence in any hypothesis then is not in accumulating evidence in its favor, but rather in showing that situations that could establish its falsity don't in fact happen. And that is something that a lot of people don't understand. They tend to think that science is gaining evidence, which of course it is, but it's evidence that is risky. You know, we want more often hypotheses are rejected than are confirmed. So, and that's okay. That's exactly what they should be. We want to make hypotheses that we can clearly say we tried to find something that could prove it wrong, and that didn't happen. Now, when you're making an experiment, and of course the hypothesis that goes with the experiment, and some of you have heard these before, you have the experimental variable, which can also be referred to the independent variable, and this is what you are testing. So this is what you are looking at, the independent variable. So maybe this could be whether or not a certain fertilizer works. Maybe this could be the amount of hormone that's needed, or the amount of daylight that signals plants to bloom, but you're testing that. So those are experimental variables, the independent variable. And what we do is we write the hypothesis including the independent variable. So for instance, here's a good example. And we write it as an if-then statement. You're probably familiar from geometry, the if-then statements. If I do this, then this will happen. And then usually you follow it with what you think is the explanation, because. And so the relationship becomes if, and then you would put your independent variable here, then you would insert the dependent variable. So if I add this certain amount of fertilizer to the plants, then I will see more fruit or have more growth. But you're measuring something. It's the dependent variable. So here's an example. If germinated and non-germinated peas are placed in similar temperature water, then more carbon dioxide will be released by the germinated peas. And then a null hypothesis. The null hypothesis is that there would be no difference. Here's another one. If there is a relationship between the wavelength of light and photosynthesis rate, then different colors will cause the plant to make different amounts of oxygen, because of course that photosynthesis is producing the oxygen. Here's one more. If temperature is related to the rate of metabolism, then raising the temperature will cause an increase in animal metabolism. And notice these are falsifiable. We can clearly prove them wrong. They're measurable. If water levels are low, then rainbow trout will suffer more lice because there's less oxygen in the water. And then so there's the independent variable, there's the dependent variable. So here's a good one. So I want you to try your hand at this. Here's a testable hypothesis with songbirds. A repertoire increases bird fitness because older birds with a larger song repertoire are more attractive to females. Well, how do we test this? What are the predictions? Well, I want you to think about it and see if you can come up with a couple of predictions. And we'll go over those tomorrow. Now, one last word on this. Notice in this graph, the repertoire size is going to be on the x-axis, and that's what we end up having. We have on the x-axis the independent variable, and that's going to be true for the vast majority. We have the independent variable, and again, that was also known as the experimental variable, and we put that on the x-axis. And then we see the dependent variable, and again, that's what we measure. That's what we're looking at, the response from the independent variable. So the dependent variable, which in this case is how long it takes them to find a mate, the pairing date. And the dependent variable is on the y-axis, and that's going to be true for the vast majority of graphs that we do where we're looking at the independent variable and dependent variable. Notice as the repertoire size goes up, so that means they have more they have more songs, they have more variations of their songs, then the pairing date goes down, which means that it takes them less time to find a mate. And that would support the hypothesis, if we go back up here, that would support the idea that they're able to get the females to be interested in them. They don't have to take a long time to get a mate. And then the last thing for now is the control variables. Control variables, depending on the type of experiment you do, these can be pretty simple, like keeping all plants in the same amount of daylight, giving the plants the same amount of water. That's pretty easy to control. We want these things to be as similar as possible, so you know the results are due to the independent variable. Sometimes they're a little bit tougher. You can imagine the control variables in an experiment like this might be a little bit tougher because you can't you're looking at sparrows of different areas and different health, and so in that instances you generally you want to increase your sample size, increase the number of measurements to reduce the statistical problems with that. But you always want to try to have as many control variables as possible. You want to try to minimize the influence against your results. Well, thank you, and we will continue this discussion in class.